Welcome to This Explainer. Look, if you've been tracking the explosive growth of AI training clusters lately, you already know we're hitting a literal physical wall. The math just isn't mathing anymore. To feed these massive GPU clusters, we're rushing headfirst into the 1.6 terabit per second switch era. And quite frankly, our current networking infrastructure is choking on the heat and the physics. So today, we're unpacking the brutal reality of this AI bandwidth wall and a radical architectural shift that's meant to solve it all: co-packaged optics. Here's our roadmap for today. We'll start with the AI bandwidth wall, then enter co-packaged optics. Next, we'll look at pluggable, linear, or near options, dive into the engineering trade-offs, and finally wrap up with the future of AI fabrics. All right, let's get into it. Part 1. The AI bandwidth wall, or why copper is dead and optics are melting. To really grasp the massive scale of this problem, consider this. A single 512-port switch now consumes up to 10 kilowatts of power, and that's literally just for its pluggable optical modules. I mean, that's enough power to run 2 entire households purely for the networking cables on one single switch. When hyperscalers are scaling up to hundreds of thousands of GPUs, they absolutely cannot sustain that kind of massive power draw. It's just not viable. So what's actually going wrong? Well, the core issue here is the SerDes breakdown. Once you hit 1.6 T speeds, electrical signals traversing a printed circuit board become incredibly fragile. Trying to salvage those extreme frequency electrical signals over copper requires massive, heat-generating digital signal processors, or DSPs. Sure, they act as retimers, but they effectively turn your optical modules into 30-watt space heaters that just completely choke the switch's front panel. Which brings us to Part 2, enter co-packaged optics, shrinking the distance to millimeters. Faced with all that heat, the ultimate theoretical goal became co-packaged optics, or CPO. Think of this as a radical architectural shift. It literally rips the optical engine right off the faceplate and integrates it directly alongside the switching chip itself, the ASIC. By putting the optics in the exact same package as the silicon, you virtually eliminate that long, lossy electrical path. Problem solved, right? Look at how this completely streamlines the signal path. Your data flows directly from the core switch ASIC instantly into the silicon photonics optical engine, across an internal fiber shuffle, and then straight out to a purely optical faceplate. Notice what's missing. There are no heavy, power-hungry transceivers on the front panel anymore. It's just pure fiber leaving the box. And the results of doing this are honestly dramatic. We're talking about a 60 to 70% power reduction and a massive latency drop, achieved simply by getting rid of that long electrical path and the DSP retimer. We literally go from 30 watts per link down to just 9 watts. And latency? That drops from a 5 to 10 nanosecond penalty all the way down to sub-1 nanosecond latency. And as you know, in an AI cluster, absolutely every single watt and nanosecond counts. Moving on to Part 3, pluggable, linear, or near. The engineering compromises. Because technology has to survive the real world, right? First up in our practical compromises, we have LPO, or linear pluggable optics. Now, this is a highly pragmatic optimization. It strips out that power-hungry DSP to keep the power draw low, but crucially, it keeps the traditional hot-swappable front panel module. It's essentially the safe, familiar pluggable form factor that network engineers already know and rely on today. Then there's NPO, which is kind of the industry's secret middle ground. Near-packaged optics actually moves the optical engines onto the host board, just centimeters from the ASIC. It definitely saves power, but importantly, it maintains what we call optoelectrical separation. Basically, it means the optics are kept physically separable to protect your extremely expensive switching chip just in case a relatively cheap optic fails. So the really crucial takeaway here is how these 3 paths represent basically life-or-death engineering trade-offs between power efficiency, signal integrity, and the very real operational risk of actually maintaining these systems. CPO? It gives you the absolute best performance, but the absolute worst serviceability. Meanwhile, LPO gives you high serviceability, but man, it demands so much more from your system to maintain that signal integrity. Let's dive deeper into this in Part 4, the engineering trade-offs, and the hidden costs of CPO. See, going all in on CPO creates what engineers like to call a shotgun wedding. Because CPO completely kills hot swapping, a single failed optical channel can literally condemn a multi-$1,000 switching chip. Think about that. If a laser or a photonic circuit dies on the package, you can't just walk up and unplug it. Nope, you are replacing the entire board. And to manage this terrifying blast radius and those painfully slow board-level repair times, data centers are forced into a corner. They have to provision expensive extra ports. Operators will typically overbuild their capacity by 5 to 10%, just so they can use software to route around hardware failures instead of immediately trying to fix them. Oh, and here is a massive plot twist for you. CPO doesn't actually remove pluggable optics from your network, not at all. It simply relocates the optical modules over to the server and the network interface card side. So guess what? You still have to buy, qualify, and manage standard pluggable transceivers at the edge of your fabric anyway. Furthermore, integrating these delicate photonic parts so tightly means testing for things like polarization sensitivity, wavelength drift, and crosstalk absolutely must be flawless before assembly. Because components cannot be swapped out once they are fused to the substrate, a single failure during final testing often means throwing the entire incredibly expensive unit straight into the trash. The manufacturing complexity here is just staggering. Let's wrap things up with Part 5, the future of AI fabrics, aligning on the 1.6T era and beyond. Despite all these brutal hurdles, we're seeing unprecedented alliances forming, like the Optical Compute Interconnect MSA. Basically, everyone who is anyone is teaming up. This group unites silicon giants like AMD, Broadcom, and NVIDIA with AI titans like Meta, Microsoft, and OpenAI. Their goal? To standardize an open, interoperable optical scale-up infrastructure. And the industry isn't just trying to solve today's bottleneck either. They are already standardizing the runway for a mind-boggling 3.2 terabits per second. When you get to those speeds, chip-level optical interconnects aren't just a nice option to have, they literally become a physical inevitability. Moving forward, we're seeing this fascinating split in how companies adapt to this. On one side, we have extreme vertical integration aimed at absolute top-tier AI factory performance, which is heavily favored by companies like NVIDIA. On the other side, open, scalable ecosystems. These open ecosystems champion NPO and LPO to protect supply chains, and they are heavily favored by merchant silicon vendors like Broadcom and Marvell. So as the AI bandwidth wall looms larger and larger every single day, which technological compromise will ultimately dominate the foundation of our digital future? Will your infrastructure risk the shotgun wedding of co-packaged optics just to get that ultimate performance? Or will you play it safe with the pluggable compromise? It's a massive, high-stakes engineering puzzle. Thanks so much for joining me for this explainer today.